perfect. All right. Just going to do a last test. Okay, can everyone hear me okay? Yeah. All right, good. Yeah, I'm good.
Okay. Good evening, ladies and gentlemen, and again welcome to one of the field chapter activities. This is one of the things which we strive to do as many as events which either are evaluating or some kind of information sharing with our field members. And those of you who know me, no problem, I'm still Rashid Khan. Those of you who don't know me, you are coming first time. My name is Rashid, and I'm the field chapter chair currently. Know that. We will be starting soon, yes, as you see already. I have a few requests, as normal. If you have still not done your search one, kindly put them to silent mode. Just check them. While the speaker is doing the presentation, I would suggest if you have to go out of the room, kindly use the door at the back so that there is a minimum disturbance. The washrooms are just outside over here on your right hand side when you go out. Those are the housekeeping announcements. And again, as you know that the agenda for today is the 3D printing. In my humble opinion, I think that there's a competition between electric cars and the 3D printing, that who will go fast, who will catch up fast in the market. So let's see in the future who is going to win. But again, the speaker is, I'm just going to read a little bit about him. The additive manufacturing refers to the process by which the digital 3D design data is used to build up a component in the layer by depositing materials. The term 3D printing is increasingly used as a synonym for additive manufacturing also. A range of different metals, plastic, composite materials, they're all used basically now to create the parts and components. This additive manufacturing now enables both design and industrial revolution in various industrial sectors such as aerospace, energy, automotive, medical, tooling, consumer, even the human parts are coming, our body parts are coming now from there. Additive manufacturing is on the threshold of totally revolutionizing the manufacturing industry. Our speaker for today is Mr. Hargurdeep Singh. He is highly knowledgeable about additive manufacturing / 3D printing. He has over 6 years of experience in the field of additive manufacturing. He is recipient of Brampton Board of Trade Top 40 Under 40 recognition, Indo-Canada Chamber of Commerce Young Achievers Award, and Ontario Association of Certified Engineering Technicians and Technologists Publication of the Year Award. Hargurdeep holds a certificate of engineering in technology. Yes, he's certified technologist designation from the OSET, and certified additive manufacturing fundamentals, which goes by CAMF, design from the Society of Manufacturing Engineers, and certified SolidWorks professions, based in Michigan, US. He's currently working as the additive manufacturing consultant at CAD Micro Solutions Inc. in Toronto, and he continues to volunteer with many organizations, including our OSET also. We are proud of him, we are thankful to you, Hargurdeep, and he's also working our chapter as a director also. So thank you, Gurdeep. But before I'm going to call upon Deep, we have a distinguished guest from our OSET office. He's a director of professional affairs and government relations, Mr. David Terlizzi. So he has kindly agreed to come over here to just say hello to you. So please help me welcome Mr. David.
Well, good evening, everyone. She just mentioned I am the new, although I'm wondering at what point do I stop saying new, being late November Director of Professional Affairs Services and Government Relations at OSET. My goal, the reason I'm here is I'm moving forward, of course, of looking at participating in as many chapter meetings as possible, getting to know obviously the members. I think you sort of live or die by your chapters, and I think it's important that obviously I sort of get to learn what's going on in these chapters. And an example like this, where I think this is probably one of the most important topics moving forward for our industry, in addition to AI and what else is happening. But this is pretty interesting. I just wanted to mention a couple things moving forward about OSET, which is pretty exciting. Number one, of course, we do have an AGM. This year it's May 30th to June 2nd. Moving forward, 2019 and beyond, we're looking at opening up the AGM and the conference in particular to all members. What does that mean for you guys? That means that you can participate moving forward when we plan into any sort of conference event. That's PD sessions. So what I'm looking at creating is sort of an event where there's technical courses, non-technical. You can show up, and in fact, we're looking at now over the summer creating an app. So imagine if you were to show up to this conference, take a course on, I don't know, maybe there'd be something on 3D additive manufacturing. Take that course, swipe it, and you've got your PD credits, which is important, of course, moving forward. The PD requirements for this profession. So that's something we're working on. In fact, the AGM this year, which is happening May 30th to June 2nd again, we're going to have an actual PD session, a 2-hour session. We're not sure at this point what we're working on. It may be about the future of work. You take something like this, AI, you wonder about what's going to happen with the industry, especially with our industry moving forward. So we're looking at having a PD session. I highly recommend that as many people attend it as possible, because I think the topic will be hopefully the future of work and what does it mean. Quickly, I was at a conference where just last year where Google was working with the company, utilizing 3D software. This will be quite interesting, I think, for all of you, whereby cooling loads in a commercial building, 8-story, cooling and heating loads, you've got your rooftop units. What would an engineering firm take to do that? Maybe a week, say 8, 9 people working together to do that. They're working on a program. Basically, you get an iPad, sheet of paper, you got a 3D model that shows up, 3-dimensional model. Well, that's pretty cool in itself, right? That's pretty neat. That'd make my jaw drop. What's interesting is it will calculate the cooling load. So let's say you make a change, turn the building 90 degrees, facing south now. That cooling load is going to increase. Back to the drawing board, right? You need a whole team to redo it. It recalculates itself. So what was interesting about technicians and technologists, what they're saying is, what's the future of work now? If I have a team of technologists who's working on that for 5-6 days, what does that mean now? It can be done in a few minutes. So that's the sort of topic what we'll be talking about going forward. So I highly suggest everyone show up that can and participate in these PD sessions. In addition, OSET's looking at now strategically creating a new strategic plan. Again, what does that mean for you guys? Well, we're wondering, what does it mean going forward for the association? What should we do? In fact, we're going to be going to particular associations. I believe Peel is one of them, that sort of go to members and say, guys, you guys are the heart and soul of this association. What do you want the association to do going forward? One thing we realized, last point, I don't want to go on here, is millennials. They are going to drive the future of this association, the industry. So we're going to be moving forward with them and consulting with them to figure, what are we doing? I mean, I look around, I'm not a millennial. I'm just going to guess that some of you aren't. So the point is, but millennials will be driving the future of the association. And I believe we have a young professionals task force. Are you one?
Yeah.
Right. So we have a task force which we're actually going to be surveying millennials. They will be the future of this association moving forward and its growth. And so we're doing a lot of exciting things at OSET. I know for myself, I'll be traveling to a whole bunch of chapters to find out, as much as I can. And I think, people like Edward Deep and this course, stuff like this is what's going to make this association great. So listen, guys, I'll be quiet now and let the professional talk. But yes.
Oh, I got a question.
I thought I was told no questions.
This is an important question that has not been addressed by OSET, and I don't believe they have one. Why don't you have an app like a LinkedIn thing with all the different disciplines? You go here, there, if you're searching for someone or something. Like we're in 2018, 2019. I don't know. Do we have an app?
So not to take away from this quickly, but all I can suggest is we are looking forward for new technologies. Understand that making apps are expensive, and something like that, I'm not sure. That's great to provide some input. I mean, we can have as many apps as you want. The point is, there's a cost associated with that. We're looking at CPD app, which I think might be more beneficial because it's a CPD requirement for our members. So look, if there's ever an idea, I mean, please let it. Yeah, absolutely. There's only so much money to be had. But again, we're open to any sort of new idea. I know I am. So anyway, thank you guys. Looking forward to this. Thank you so much.
That was a good suggestion, and I'm sure it will come back. I think when David goes to office, he will surely put the other point over there.
We'll have it done next week.
Maybe in a year or two, but it should
Maybe
be
we can.
coming
Yes,
sooner
yes.
than that. Yeah.
So we are about to start. But I will request you people that if you see that any seat is empty, so I will suggest that you move towards the aisle, like inside over there, so that if anybody comes late, he will take the corner chair. So like here, if one is empty, if you just, ma'am, if you can just move it on this side, so that just gentlemen, so that if anybody comes late, he can just sit over there on that side. So nobody will get disturbed over there. You just move a little bit on this side, you just move on this side.
Just to move in together.
Sir, you can move on this side. Sir, you can take the chair. Yes. Somebody sitting here. Somebody sitting, I'm sorry. So, okay, without wasting any time, I'm going to invite the speaker of the evening. So please help me welcome Pratmati Singh.
All right. Well, hopefully this works. There you go. All right, everything's working. Good. Okay, good afternoon, good evening, ladies and gentlemen. Thank you, OSAT Field Chapter, for once again having me here. It's always a pleasure to work with this organization. As said, I've worked in OSAT with the council representing the students across Ontario, and I'm helping out as a director in the Field Chapter. Just with a raise of hand before I get started, I did a conversation similar to this related to additive technology or 3D printing about a year back. How many people that have attended that talk are present today? Just with a raise of hand. Okay. The AGM was one, yes. Okay, good. So that's good because part of what I'm doing today in the presentation, I'm doing a little bit of recap initially to get you guys up to speed about what is additive technology and a bit of a recap. And then we'll jump right into how it's disrupting and impacting the next industrial revolution. Another question, just with a raise of hand, how many people are currently using 3D printers? Whether they're outsourcing or they're printing in-house? Okay, good. Fantastic. Okay, and how many people are in the automotive industry? Okay. How many people in the tooling and jigs and fixture type applications? Okay. How many people in consumer products? Electronics? Civil? Electrical? Wonderful. Okay, good. So we got a wide range of group here, so that's great. Additive manufacturing is impacting at every single industry, as we know. Time to time, I get people ask me a question. Usually it's at the end of the presentation where, Deep, I don't see an application for our industry, and then it's really hard to kind of challenge 3D printing at this point to figure out if there's no application in that field. Typically, we prove people wrong. So it'd be interesting to see if you guys have questions and you have some applications where you have yet not seen 3D printing. It might be that you're not aware of it at this moment, and a lot of things are happening on the back end. As Rashid said, that with 3D printing, you're now printing human body parts as well, right? So it's gone to a point where it's just plastic parts. Okay, so what I'm going to be talking about today, I'll talk about Industry 4.0, the past, the present, and the future, and where it's heading towards. I'll do a recap of additive manufacturing 101. So time to time, you're going to hear me say additive manufacturing. And additive manufacturing, just another word for 3D printing. I like to use the word additive manufacturing because it covers a wide range of different processes and technology that 3D printing has to offer. So don't get confused if I'm saying 3D printing and additive manufacturing means the same thing. Okay? Additive manufacturing applications. So I'll talk about some of those applications that are existing today and some of the applications that you may have seen around and some of the new applications. We'll talk about different technologies and different processes. And then we'll jump right into HP's multi-jet fusion technology. And the reason why I chose HP for today's talk is because HP is truly creating production-ready equipment where you can print hundreds, if not thousands, parts a day. So it's no longer, for some of you guys who have experience with 3D printers or that you're printing right now, you might understand the process is extremely slow. It's taking several hours, several days to produce the parts. But it's past that point. We're now printing hundreds, if not thousands, parts a day, and HP is truly positioned to take over or penetrate into the $12 trillion global manufacturing market. So that's why, I'll talk about the additive side from HP. I'll do a live demonstration if time is available. What I'll do is I'll do a CAD design. We were hoping to do a print, but we were in a rush. We had a lot of meetings happening today, so we forgot the build tray where the part prints on. So the print won't be possible today, but I do have a sample of that particular piece that I had in mind that I was going to print. And there's lots of examples up front, so if you guys have time after the presentation, you don't really understand what those parts are, I'll be around. My colleague Cyan back there, he'll be there, so feel free to ask him questions if you have anything around those parts. And in the end, I'll talk about some case studies and open discussion for any questions that you guys may have. I'll try to address as many as I can as time allows. Okay. So, getting to the point, what is Industry 4.0? The past, present, and the future. Well, Industry 4.0 is just another fancy word for industrial revolution, the fourth industrial revolution, right? We have faced 3 industrial revolutions. Currently, we're in the 4th one. In the 80s, you got the mechanical age where steam power equipment was existing, right? And then the 90s came around. Then you got the assembly plant, right? So mass production with Ford, the assembly line started coming across. The 3rd industrial revolution that we just passed in the 20th century, that was related to product automation, where you saw robotics, you saw the internet era, you saw computer and those type of applications. And now the 4th industrial revolution that we're in right now, this is where you're seeing digital manufacturing, smart manufacturing, right? There's a lot of words that people like to use for industrial revolution or the industrial 4.0, and some of them say, smart factory, factory of the future, right? That's what we're talking about. We're talking about digital manufacturing. You'll get to know about digital manufacturing a bit more as I go on into the presentation. And how to be capital efficient, right? And how to increase efficiency. How do you drive manufacturing based on data-driven application, right? It's no longer a time where you got a draft person and you got a big room where he's lying on the floor and creating these sketch. Everything's done digitally. You can create massive buildings and all that information just from sitting on your computer, right? And you have every single detail involved. Another phenomenon that we hear is digital twin. So everything that we see around us is going to have a digital twin, a copy, a digital version of that. I can tell you right now, my wife and I, for our anniversary, we got a figurine done. So we got a digital twin of ourselves already. Okay, so just to kind of go and show you, there's going to be a copy of just about everything. As we see Google Street View, we see more products, we see chairs, we see these kind of events. It's going to be all a digital copy and in 3-dimensional copy.
Digital twin?
I'll go more into it. Questions for the end, please. I just want to cover as much topic as I can. So some of the examples that you saw in the first industrial revolution, you saw the steam engine, sewing machine, telegraph, loom, power loom. Hard to see that we've come such a long way. I remember my grandma using sewing machines and stuff like that, right? But that was your first industrial revolution. The second one came around, you got the assembly line, you had the plane, the first induction electric motor telephone. This is how it looked like, when it first came out in the 18th century. Then this was that big boom where we got to see the desktop computer, we got to see integrated circuits, cell phone. Can you believe that was a cell phone? My son would not know this was a cell phone if I show him now. Space shuttle launch, that was a big one, right? And you had the first Boeing, internet. What was interesting was in the 20th century, you had the first 3D printer that looked like that. right? And it was meant to do prototyping. And only the people that were able to afford such an expensive equipment had access to use this type of equipment. Now I'm walking around with that piece of equipment in my car, right? And you see that in the back there. And it's probably able to do a lot more applications and functions than it did when first it was invented in the 1986. So this was when the prototyping system came out. It was made out of liquid resin, and the part will get cured with UV light, and you saw part becoming solid as a three-dimensional solid part. But that was one set of process. Many, many different processes around the additive technology has evolved since. So what's happening now? So fourth industrial revolution, so digital manufacturing, what's going on, right? So, with man trying to go more towards space and Mars, right? You're starting to see some of those type of stuff. In the 1997, you saw the Mars Pathfinder. First smartphone came out, Bluetooth headset. Cloud. For many times, a lot of people were confused. What is cloud? And I think there's still a little bit of confusion around there. But cloud was a 2008 invention when you were able to take digital file and send it up into a cloud format. Who remembers Felix, the guy who jumped out of space? Broke the sound barrier. That happened in 2012. That is still in the fourth industrial revolution. But this is where it starts getting interesting, right? As we're starting to move towards, what is now. In 2016, first FAA approved 3D printed jet nozzle was created. So think about this. A century before that, we were still in prototyping. Now we're getting into mass production, 3D printing mass production of GE's #1 selling engine. And they're 3D printing components inside that engine. And it's FAA approved. And then 2017, HP came out with their production system. That's how it kind of looks like. Takes up pretty much half of this room here at the front. Quite a big system. And that was 2017. And recently, how many people with a raise of hand saw that Falcon Heavy go up? Yeah, that was groundbreaking, right? So in Falcon Heavy, in that spaceship that just recently SpaceX released, the thrust chamber inside that Falcon Heavy was 3D printed. Isn't that incredible? Like, we went from just a century before, from prototyping to mass production to creating parts. They're going up in space. That's where 3D printing is today. That's where the additive technology is today. We're no longer at a point, simple piece of plastic. Right? There's a high value that's coming out of this. So where is 3D printing heading? Like, why is there barriers? Like, why are people not adopting to it? I mean, with a raise of hand, when I asked originally how many people are using 3D printer, I saw maybe 4 or 5 hands maximum go up in a room full of people. There's a lot of barriers to it, right? And some of the barriers is, you have, I went straight to the barriers. I'll talk about it after. I didn't realize my slide is off. But there are a lot of barriers. But what I want to talk about before the barriers is that there are, in Industrial 4.0, there are about 5-6 different technologies that are emerging. You got artificial intelligence, you have Internet of Things, big data analytics, robotics. Out of that, 3D printing is the one that's kind of leading, and there's a maximum potential there. And the maximum potential for 3D printing is there to disrupt $12 trillion global manufacturing market. $12 trillion with a T. And what's it able to do? It's able to do rapid innovation. So as you're designing, there's a speed for everything that you develop today, right? So the quicker you're able to manufacture, the quicker you're able to design, the quicker you're able to prove out, the quicker you go into market, the faster you make your money, right? So 3D printing helps you do that. It helps you do rapid innovation. It shortens up your time to market. It's able to decrease your inventory. You're not going to believe that. I see companies on my daily basis, and they're holding $3 to $5 million on an average inventory, where 3D printing is able to eliminate that. You have a machine, if your parts break down, you press print, you now have parts, right? So inventory management, inventory control is going to be good. Overall, you're going to get more efficient. The supply chain is going to be disrupted. So think about the carbon footprint. If you got a 3D printer located at sites, right? Think about how we order stuff now. We order things from internet. A lot of the stuff that I brought in today, I've ordered from Amazon, and it was shipped to my house. Now, it took a day or two to arrive. And as we need things more quicker, guess what? If you have a 3D printer and you order something and the 3D printer is close to your location, if it's in a community center, like where we are today, you just go to a community center and the thing just prints for you and you just get it up over the shelf, or a drone drops it off, right? That's where we're really, it's no longer fictional. That's where things are really heading. You know, we're seeing companies evolve and adopt to these types of things. Ultimately, it all comes down to higher capital efficiency, right? How are you managing your money? Where are you getting in return? So, you know, if you look at this circle right here, you look at the $12 trillion number. That's a global manufacturing sector. If you look at this ball within that circle, that's where 3D printing is right now. A couple $1 billion investment. Look at the potential that the additive technology has. So it's just at a starting point. It's not able to get into that big manufacturing sector. And part of the reason, like I started earlier, there are some factors that are holding 3D printing back. And there's about 6 factors. One is product capabilities. What can your 3D printer make? Right? The material selection, material pricing, right? The cost of the material has to go down in order to unlock this capability. And how can all that be accelerated? How can adoption for 3D printing how can that be accelerated? In order to accelerate that, you have to learn and think a new way. You have to learn how to design for additive. You have to learn how to think in 3-dimensional, right? So that needs to be accelerated. So school has to develop curriculums, companies have to adopt, and design for additive, there's a new way of thinking. New supply chain have to come across, right? Additive is releasing a 3D printed shoe later this year, right? So they're disrupting that. You'll be able to buy it. And standards and policies have to be created around this technology, right? Until you got some numbers on some standards, some policies, it's really hard to put it in place as an end use. But like the previous example, you saw FAA approved for the jet nozzle engine, for the LEAP engine for the GE. So they are working towards it. You know, the rate of that has to increase. Okay. So how's HP kind of positioned to disrupt all that? How are they able to, you know, take those key factors that are currently a bottleneck in the additive adoption? What are they doing? So what they're doing is, one, HP is partnering up with the people that already know their stuff, right? They're not trying to reinvent the wheel. So they're partnering up with the best of the best. They're already in the space. You got BMW, other companies that are engaged. They're partnering up with the specialists. They're doing that. But what's kind of exciting, and what I thought, you know, when I think about HP is, HP, when you buy a regular 2D printer that prints off on the paper, but then you have to buy materials from them, you're kind of locked in, and that's kind of like the ecosystem. HP went completely opposite when it came down to 3D printing. They partnered up with over 50 material leaders around the world and told them, hey, we're going to make the printer. We're good at our existing technology. We know how the nozzles work with our regular printer. We're going to take that and put it into 3D technology. But we're not good at making the material. So if you're good at that, we're going to partner with you. So they partner with over 50 companies across the world, and their task to do is develop different materials. So as more materials come out, the price of the materials go down. That, when bottlenecks, gets unlocked, right? So that's very interesting. And they're partnering with over 65 resellers across the world, and putting 25 reference centers globally where people can see what this technology is doing. So they're really pushing it forward. I want to wave to Ian Durbach back there. He's a channel business partner for HP. Thank you for joining us, Ian. He'll be around, so if you guys have questions around that HP Pacific, he'll be there. So that's quite interesting. So the current limitation, again, you know, it's your production time. We talked about it. You got a 3D printer. It takes hours, it takes months, it takes weeks, right? It's a slow process. It's going to be hard to adopt. So there's definitely a limitation. The quality of the parts, right? They're poor to fair. They're not like the parts that you get from your injection mold capability. Like the quality isn't just there. right, for 3D printing. That's also a limitation. And then you got your production process. It's open loop. Anyone can kind of enter in, low part consistency, right? How many times do you get that same repeatability if you were to print one part or 100 parts or 1,000 parts, right? So those are some of the limitations right now. So with HP's open platform, as they're partnering up with other people, they're concentrating on speed, quality, cost, and reliability. Those are kind of the key factors that they're concentrating on to penetrate into the additive market. And they're doing that by democratizing 3D printing and opening up a broad spectrum of 3D printer. For some of you who have experience with 3D printers, some of you guys who have seen maybe industrial printers, you've probably seen a figure of 3D printers anywhere from $500,000, $1 million and beyond to get a very decent sized industrial printer. So HP's democratizing that by having access to a printer for only $50,000 to $100,000 range for their color and full color printer. With that, you can print a wide range of different applications, full color, plastic parts. As well as they have created their production facility, so if you're making parts that are more than 130 parts a week, then you go for a production run. But not everyone's going to be able to go for that production. You still have that early prototype or small wrap-up production. So for that, they've covered up that area as well. But again, they're targeting speed, cost, reliability, and dependability on the machine. So that's kind of where first industrial revolution was, and it's kind of transitioning. We're now seeing 3D printing as one of the key leading element in the evolution of the next industrial revolution. And HP is kind of playing their role and making that come out really fast. But what I want to target now is, understand what is additive manufacturing. This is a full seminar on its own, but I've kind of condensed the slides down to kind of go over some of the work that I've talked about in the past. So if you guys do have questions around this, again, I'll be able to answer them at the end. Okay. So additive manufacturing, according to American Society of Testing Materials Standard, the definition is a process of joining materials to make object from 3D data, usually layer upon layer, as opposed to subtractive methodology. Right. So what does that mean? What does that mean exactly? So on the left side, you see a picture. This is an additive picture. You can see a ceramic layer, a concrete layer, built layer by layer by layer. There's material that's extruding down. This is actually currently happening. There are companies that are printing houses, believe it or not, with concrete. And on the right side, you see a traditional subtractive process where you start with a homogeneous material and you subtract it until you get a desired shape, whether it's a CNC or a milling process. Right? So, difference between additive 3D printing versus subtractive. And how do you get a part? How does a printer work? Is it just a push a button? How does the printer understand? So typically with any 3D printing technology, there's about 5 processes, 5 stages, right? The first stage is you start with a CAD model, computer-aided design. So whatever that software may look like. Then you save that into an STL format, and I'll get a little deeper what that STL format is. Then it goes into a slicer software, and then it goes into your 3D printer, and a finished part is ready. So I'll break that down for you. So, you start with your CAD model. It could be a wide range of these softwares. With a raise of hand, how many people can identify some of the softwares here that they're using? Okay, so a fair number of you. And a fair number of you guys are using the software, but you're not using 3D printers. Because I can see the same hands go up. So that same software that you're using, you're creating the file already that can be used in a 3D printer. It's that simple, right? So once you have that CAD file, it is then converted into an STL file. An STL file stands for stereolithography. There's different names for it. It stands for standard triangular language. It stands for standard tessellation language. Really what it is it's a file format that from a CAD software that you can export that a 3D printer is able to understand. So when 3D printing, when Charles Hull, the founder of 3D Systems in 1986, when he was creating the 3D printer with that photopolymerization process, liquid process. There needs to be a language that a printer can understand and the software can communicate. So they developed this language at that time. The STL file format over the time has become a standard 3D printing file, although there are other files that can be used, but STL will get you from every printer. It's like a PDF equivalent for 3D printer. Okay. Then it goes into a slicing software. And what does that do? So slicing software, so when you're printing a document in 2D, when you're printing just a piece of paper, typically when you press file print, a window pops up, some sort of driver. It tells you how many copies do you want, how do you want the paper to be printed front and back. Similar to that, a 3D printer also has its own driver software. And typically it's referred to as a slicer software, right? And it has many different names for depending on which manufacturer you're using for your 3D printing. They may have different names assigned and they may have some IP related to their software. But at the end of the day, what it's doing is essentially the same thing. It's taking your 3D data and it's converting into 2D slices. Okay? So if you think about a loaf of bread, right? You cut that into slices, and if you were to place one slice on top of the other slice, on top of the other slice, you'll see the full bread again. All it's doing is it's doing that and it's fusing each bread up to the other bread, right? So that's what you're getting. Some of the controls you get in the software, you can control how you're going to build the part. Which, is it going to be facing up? Is it going to be turning left? Is it going to be facing right? And a lot of that is going to affect your part surface finish. It's going to affect the cost of your part. How long does it take to print? So there's a key consideration and a learning curve when you're considering this process parameter setting. Design for additive is one thing, and then processing is another, right? So there's a bit of a learning curve for sure, depending on what technology you're with. You control the part density. This is really, really cool. So what part density does is, typically we see, anything that's cut from subtractive technology, you cut away from a block, it's still solid. With additive, you now have the capability, whether you want to have, different type of patterns inside your parts, whether it's honeycomb, triangular fill, hexagonal fill, and so forth, and outside you got a closed circuit, or this new powder bed fusion technology that HP is doing or other companies are doing, it allows you to manipulate the exterior as well to create more lattice geometry. So you can create geometries that just weren't possible before. Right? To give you an example, if you think about like an interconnected chain, think about that completely printed without any post-processing. You print something out and it's fully connected, interconnected. You get those capabilities with additive. Actually, with additive, the complexity of the design comes for free because the machine doesn't care what you're printing. You can print complex parts that traditionally would require multiple processes and subtractive technology, but with additive, you can just print that as one go. And we'll have some parts that I can show you. I'll pass some parts around, so you guys are kind of checking it out. I'll pass these two just to kind of start off. This is a zip tie. This is 3D printed. So I'll pass that around. You can see there's some flexibility. What's interesting is I'm going to pass this keychain down, and I'll collect that later. Please, this is my only one. Typically I have people that have found a lot of interest and walked off of it. So this is my only one. What you will find is that there's multiple parts, and it's printed this way. It's not connected afterwards. There's no post-processing to connect these parts. They're printed and came out of the machine just like that. Now scale that into different applications. You can have so many different variations that weren't possible before. Right? That's exciting. Okay. Layer thickness. So how thick are you printing your parts? What kind of structure are you going to create? How your part's going to be supported? All of that is accessible through the slicer software. Right. Then comes the easy stuff. Then is your hardware. On hardware, you load in your material, whether it's powder, filament, or it's resin, depending on the system you're using, and you press print, and the machine does the rest of the work. Right? So a lot of times, my machines that I'm using, they can be connected on the cloud. So if I'm traveling, if I'm overseas, or if I'm not in the country, or if I'm somewhere else, as long as my machines are turned on, they're connected on the internet, I can send parts to my machine like fax. So when I come back from a trip, there's a part sitting in my printer. That's how cool it is, right? So yeah, so add in the materials and then it prints your part layer by layer by layer.
That's
Okay.
a stress-free way to work.
I don't know if it's
No,
stress
wait,
free.
come back.
I think efficiency adds on, a bit more stress, but someone can debate that for sure. Then comes post-processing, right? Post-processing, this is interesting. So depending on technology, there's different type of post-processing, right? This is an example of material extrusion type of process. So what you're seeing is this white material here, that's your support structure for any overhangs, right? And simply either you can break it off and you can put it, or you can put it in a chemical bath where that material gets dissolved away, so you're left with complexity. HP does not have that. HP prints with powder, so support material just falls right out, right? So the material that you're using, here's another good point. So the material that you're using can be recycled. It's a ratio to 80% old and 20% new. So you're only using the material that you need. Rather than in subtractive, you start from a block, you cut it and you trim it away, and you're wasting a lot of material, right? Again, it goes back down to how to be more efficient, but how to be more sustainable in our green energy, right? And then you can do some post-processing. You can sand them, paint them, just like you would do any other part. And here's a wonderful example of a very complicated piece that is finished, 3D printed, then post-processing, painting. And typically, if some of your favorite shows, if you're watching, you will find costumes that are 3D printed, that have very unique capability, that are just not possible to make any other way. Those days are gone when you had somebody sitting there and sculpturing through these type of projects. You still have those people, that's a very big talent, but it's hard to find those type of individuals, right? So now if you can translate that, manual work into digital data, you can then print that and have very, very complex parts, right? And this can be all printed as one piece. So additive manufacturing applications, right? There's just wide range. I would need at least 2-3 days out of your time to go through some of the applications, right? It's just wide range. Whether you're in aerospace or you're in security and defense, right? One of the applications for security and defense, for example, you don't want your intellectual property to get lost, right? So if you're working on a project, you send it to someone else, and there's your data, it's gone, right? So if you have a 3D printer, you have additive technology, you have control over what you're doing in-house. And that could apply for all of the industries. Some of the examples, this is a this is a lever that's in the planes, made out of metal, right? The capability of this is that unique lattice structure. You're seeing those geometries that are kind of complex. And the reason they did that is they used a methodology called topology optimization, where you optimize where the strength is required, and the computation background of the computer will subtract away any excess material that you're using. And in your 3D printer, you will only print what you need rather than printing a block-like structure, right? Shoes, Adidas is coming up with the shoes, like I said. Dental implants, that's a big one, right? Because it's all customized, it's unique, right? How do you do mass customization? You got people with unique capabilities, unique teeth. They're 3D printing these with titanium. Just the other day, I shared something on my social media. The first surgery that took place, doctors in, I believe it was Germany, they 3D printed titanium ribs and performed the first surgery. Hip replacements, knee joints, all of that stuff's happening, right? Injection molding. I think 90% of the hearing aids that we get now are 3D printed. Did you guys know that? It's cool, eh? So, there's obviously a lot of different applications, a ton of different applications, and if you go about and you start investigating how you're going to bring 3D printer in your facility, or how can you leverage this technology and be on the cutting edge, it's kind of overwhelming. It's hard to make a decision which is the right technology, where do you start, right? I usually make a recommendation around, start from your machine shop. That's where you're going to find immediate return of investment when you go into 3D printing. Your jigs, your fixtures, your soft tooling, robotic fixtures, all of that, your machine clamps, all of that can be 3D printed. I got an example of some of these parts over here. This is an interesting case. I'll show you guys here. So this is a CMM fixture. You guys are familiar with CMM? Coordinate measuring machine. It's used for quality inspection. It was made out of, aluminum blocks. It was about 15, 16 different pieces. And it would take, the quality engineer about 5, 10 minutes, 15 minutes to assemble that part. Now, this little piece right here, that black piece that you see, that's entirely 3D printed. Now it takes less than, 5 seconds. Lock it up, and it goes, then you run your program. So if you start from your machine floor, if you start from, some of the welding fixtures, if you're doing a lot of welding, if you're doing some of the machine floor work, that's where you're going to find an immediate ROI. And then once you start picking out those applications, you got some trial and error, then you can move into some of the bigger ones. These parts are printed with carbon fiber reinforcement. So some of those parts are actually stronger than aluminum, which is cool. Aluminium. And if this is not what you're interested in, and you're definitely shooting for something high, and you got some parts that you're manufacturing right now using injection molding process, here's an example. You got this one duct system, and it's taking multiple different components. All of that sourced somewhere else, and it all comes together, or it's sourced at the same company, multiple tooling costs. You can then now 3D print that as one piece. So there's no tooling cost, no assembly and testing required. You got a simplified supply chain and qualification, and you got a time saving for your designer. How many times, as a designer, you have designed parts that are sent out and then they come back and they don't fit together? It still happens, right?
Yes.
Yeah. So if you have that capability to do those testing in-house, think about all the time that you're going to save and all the money that you're going to save without investing into tooling. Right? That's where digital manufacturing is really helping out. So, additive manufacturing technologies, like I said, it's no longer just one type of process. It's no longer just extruding material. We have a machine that falls under that we brought today. It falls under here. It's hard to see. FDM, fused deposition modeling. That's a type of 3D printer that you will commonly find around where material is extruding. But there's about 7 different processes, and under those 7 different processes, there's like 12 to 14 different technologies. So there's a wide range of 3D printing technologies. That's why the word additive manufacturing is getting around, because you can create parts differently, and not every machine is meant to do everything. So you're going to have one machine that's going to be good at strength, other machine is going to be good at complex parts, other machine is going to be good at different materials. So there's a lot of different options available. Under all that, if you look at powder bed fusion, multi-jet fusion, the only company that's figured that out is HP. So they got it pretty locked tight right now, right? So they're doing some really good stuff in the powder bed fusion. And this is what their printer looks like. So you got a 3D printer. It comes with a software, the slicer software I told you, the utility software, right? And this is the build part. This is where your part gets built in this area. It's almost like that cart that when you get a flight attendant to walk around. It's almost that size looking. And then you got a post-processing station. This is where any unused material gets recycled and back into this machine so that you can continue your print without waste. It's a complete loop, so end-to-end solution. And how are they able to do that? So what are they doing? So HP, they start off with loose powder and apply different agents. So they got fusing agents that fuses the powders together, and then they got detailing agents that creates detail around the perimeter of the part. So if you saw that little piece that was passing around, you can see it's quite detailed, right? So the only way to keep that reliability that they're focusing on and repeatability is by applying different agents. And then there's a heat source or energy source, which is a lamp that fuses those layers together. And ultimately, you got a finished part. Okay, so hopefully this works. It's supposed to be a video. Sure. Oh, no, good. Okay, I'm not sure what's happening there, but I do have it in my folder, so we'll just cheat our way.
HP's multi-jet fusion technique.
So this video is going to talk about the process. So you get to see you're not seeing it there. I'm seeing it here. One second. Okay. Yeah. Good. So here you're going to get to see the process, how 3D printing is actually happening in the powder bed fusion, and what that technology looks like.
HP's multi-jet fusion technology produces quality, functional parts at a production speed which is up to 10 times faster than today's competing products. Unlike the slow point processes of some current technologies, HP's multi-jet fusion technology processes parts in 2 fast, area-wide passes to achieve top-speed part production. The process begins by applying a layer of material in a work area. In the opposite direction, in one continuous pass, we print fusing and detailing agents across the full working area. This pass combines the printing with the fusing energy, and the process is then completed. HP's proprietary architecture is capable of printing 30 million drops per second along every single inch of bed width, enabling extreme precision and dimensional accuracy. To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, a fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer. HP Multi-Jet Fusion's closed-loop thermal control system does this by measuring temperatures at hundreds of points on the material bed. This information then determines which areas receive more energy to raise the temperature and which areas are cooled, allowing for control of thermal bleed and layer-to-layer fusing and cooling. The result is full control over mechanical properties, dimensional accuracy, and repeatability. The process is then repeated until a complete quality, truly functional part has been formed. This is how HP's proprietary area-wide processing compares with existing popular point processing technologies for building functional parts. In the time it takes these slower point processes to build 1,000 parts, HP's multi-jet fusion technology would have created several thousands of parts. Using HP's proprietary multi-agent printing, the HP multi-jet fusion technology achieves new levels of part quality at these breakthrough speeds. In 3D design and printing, a voxel represents a value on a regular grid in a three-dimensional space, like a pixel with volume. By controlling the properties of each individual voxel through agents, HP Multi-Jet Fusion can produce parts that can't be made by other methods. Taking advantage of HP's in-depth knowledge of color science, HP's 3D printers could in the future selectively print a different color at each volumetric pixel. A single 3D printed part could have literally millions of colors. But more than just full color printing of functional parts, HP's multi-agent system enables a fundamentally different approach that could unlock the full potential of 3D printing. At each voxel, HP transforming agents could control surface texture, wear, and friction, enabling single parts with multiple textures, or the monitoring of part performance. The transforming agents could control the translucency of each voxel, enabling the printing of lenses or sensors. We could also optimize the strength and stiffness in portions of a part and print elastic voxels in other portions of the part. The conductivity of certain voxels could also be controlled, enabling embedded electronics. HP transforming agents could also be used to enable the printing of new advanced materials, or enable emulating different materials at each voxel. HP's multi-jet fusion technology could enable design and manufacturing possibilities that surpass the limits of our imagination.
Okay. So, what do you guys think so far? It's crazy, eh? I mean, with the voxel level control, I'm not sure if you guys heard, the voxel is basically a volumetric pixel. Imagine if you can control every single pixel on your part. You can have endless options of how that part looks like. You can have integrated circuits, translucency, different colors, all of that million different times in that single part. That's great. That's why I'm in this profession, because I just love this technology. I get so excited with seeing what the technology is kind of leading towards. You guys recognize this little print head? You probably saw that in your inkjet printer or something like that. Well, that's exactly what HP is using in their 3D printers. This is what they're using to deposit those million little dots per second that are fusing the powder. And then the heat source is fusing that. So what you're holding in your hand when that part was going around, that was printed using this technology. Pretty solid. So they've always been in 3D printing, or they had the technology to do that, just evolved as the demand grew. Okay, so what I wanted to do now is I wanted to create a design for you guys and print that out, and so you can see what that STL file looks like. What that process of design for additive manufacturing and then printing and all that looks like, right? And do a bit of total cost analysis and print that part out with the printer, but I don't have that printer operational right now. I forgot that build tray, but we'll skip that, but I think I still have that part somewhere. Yes, I do have that part, so that's where I'm good. So I'm going to use the software. It's called SolidWorks. I have access to this one, so that's why I'm going to use this. You can use any CAD software, computer-aided design, and a few of you guys are already using that. What I'm going to design today is to solve a real problem that I have related to a really dear and near item that I have in my house that's always getting misplaced. It's called a slide and a bodge. For those who tie a turban will know. And you can probably attest to that, right? This is that instrument that helps me keep my hair tucked in and make my turban look nice every single morning. But every morning when I wake up, I find this misplaced. Either my wife, she used it last night to keep her hair up, right, tight, or someone else has used it to open up the letters. So I never find it where I want this to be. So I have a real problem, right? So how do I solve that? So I decided to create a bracket just for this slide so I can screw that in my washroom so that there's a dedicated place, okay? This is a real problem. But I didn't want to go through the entire injection molding process. So what I did, I'm going to use 3D printing. And let's say out of this I develop a business. And sir, if you want to be my first customer, open for business. So if I start a business line with this new invention, and while I'm making this, think about some of the capabilities or possibilities that you can take that and translate that into the manufacturing world. So if you're designing a new part for a car, for example, right? What that process may look like for you. You may have to design the part, you may have to send it for tooling to get injection mold tooling, you may have to then get the part produced, and then you look at your cost, and it's just adding up as you're doing revisions, as you're modifying those changes. I'm going to take that same car part and I'm going to keep it for something that I'm actually having some problems with. So I'm going to try to fix that. So I'm just going to quickly try to cap this up, or just to save some time, I'll open up the file that I already kind of designed. So this is a little small bracket, nothing too exciting, but it's going to solve the real problem that I have, right? So this is that little bracket that I designed. Probably took me 5 minutes to create that in the software, and then I have a digital copy of that. What I'm going to do then at that point is I'm going to save this as an STL format. So I go save as, I find the right format. Sorry if those who can't see me, sit down. Here you can see an STL format, and I'll press save, and I already have that saved, so I'll just kind of do that again. What I want to show you at this point, remember I told you that STL stands for Standard Triangular Language or Standard Tessellation Language? What it did to that part, it created a lot of different triangles. What are we looking at in terms of number? So those who are at the back will probably read 5,020 triangles off that CAD data that I just created. So everything that gets converted into STL gets converted into these triangles, and you're looking at about 5,020 triangles for a small little bracket. Once I'm done with that, I go to my printer slicer. So this is my printer slicer. I define what material I'm going to print in. In this case, I have option to print in onyx. Onyx is a nylon with chopped microcarbon fiber type of composition. It's a plastics stuff that you saw. So if I look at that and I define some of the parameters how I want to print, my cost to print this is only 36 cents US. 36 cents. And how long? It's going to take 40 minutes. In 40 minutes, I got a part. In 5 minutes, it took me to design. In 40 minutes, I have it printed. In 45 minutes overall together, I have this problem that I had solved because it's now in my washroom. But think about it. Now, take that same idea. Remember I told you, think about it from a manufacturing standpoint, right? If you were a guy who's developing a part for the car, you just eliminated all that tooling type of cost. In just a short matter of time, depending on the technology you choose, you can have your piece in front of you. You know, it used to take years to design a car and have it out in the market. Now it only takes months. And most of that is because they have to put together the assembly line. That's where the cost is, not in the design. So it's quite interesting. So if you're kind of happy with that, let's say I get a business going and I got my friend here, he orders a bunch of them for his friends, right? And I want to print multiple of these. I want to see in 24 hours, I can print, let's say, multiple of these. Let's see what the number is in 24. So as I'm multiplying this. So in 24 hours, I'm looking at 39 brackets. So, let the printer run for a day, come back, and I got 39 of these, and I have no inventory that I have to keep. As I get orders, I print and I ship out. But, in the manufacturing world, this doesn't make sense. Like, I'm not going to run a successful business if all I'm getting in 24 hours is, 39 of those. Doesn't make sense, right? Should be in a higher volume. Should be getting like 5,000 of those a day. And then that's where then you start thinking, 3D printing is really not efficient because it's taking you 24 hours to print 39. How can you be efficient with your technology? This is where I'm going to open up the slicer for HP. This is the technology great for some of the parts that you can produce for early stage and all that. But now business is doing great, right? I'm getting this 5,000 part order every single day. So what do I do? So this is that slicer for that. Let me add the part. So same STL file. and do an auto fix. There was some issues with the steel triangle. So I got the same part, right? The beauty of HP is no matter what you put in this build envelope, it's about 15 by 16 by something. I have the numbers. We can share that with you. Whatever you put in that, the height is about 15 inches. It takes about an hour to print an inch in height, but it also prints in your X and Y. So you can have whatever you can fit in this in 24 hours. 15 hours, sorry. 15 hours to print, and then there's a post-processing. So overall, you're looking at 24 hours. So let's see how many of these parts can we print in 24 hours. In the old one, as you remember, it was 39, I believe?
Yes.
Okay. And then let's say fill the build volume. So it does computation behind back end. The software's figuring out, how can I mix different parts in that space. And once it's done all that,
So HP are offering hubs like that you can go and pick the parts up?
not at this point, but there are companies that are buying the machine to do that.
That's what you were talking about. They're offering that service right now.
They're offering the printer. Right. So in 24 hours, you're looking at 5,000 parts, 4,998. Right? That's 24 hours, where the other one was 39. So now 39 versus 5,000. Now that could be successful. But now let's do some study in terms of how much is it going to cost me for tooling and how much is it going to cost me for 3D printing overall. Because remember, the cost was about 45 cents per piece. What is this costing me? So what I did, I reached out to a injection molding company and I got them to quote me. This is actually their quote. I just took a snapshot. And I asked them to quote me 4,998 of those parts. What would be my tooling cost? What would be my end part cost? So my tooling cost alone was about $3,000 Canadian. This is without me even having the part. And they said it was going to take about 15 days to create the tool for this part. And then the part cost after that drops down. It's about 33 cents per part. The other 3D printer was about 45. So part cost does drop down, but your tooling cost is significantly higher. Overall, this project would cost me about $5,000 plus setup cost and shipping and so forth. So by the time I get those 5,000 parts, my customers are already 15 days